Okay, lecture 57, hypothesis testing for variance or standard deviation examples. Example 1, Creamy Cream Dairy is concerned that the machines that fill their gallon jugs of milk are showing too wide a variation in the actual amount of milk they put into the jugs. They would like to keep their standard deviation to no more than 1/4 of an ounce per gallon jug. If it is more than that, they should probably work on the precision of their process a little bit. So they want to see if they need to do that. So you're Creamy Cream's resident statistician, and so you conduct a hypothesis test to determine whether the standard deviation of the gallons of milk is too large. And so assuming, remember, that the population of weights are normally or is normally distributed, we have to make that assumption before we do this particular test. With a standard deviation, sigma, of these gallon jugs, your null and alternative hypotheses are, all right, you're hoping to be able to say that, how is it worded? It says here, you don't want the standard, you want it to be no more than 1/4 of an ounce. So certainly H1, the alternative hypothesis is going to be that it's greater than. No more than, we could write that as sigma being equal to 1/4. And I say here that you could also say, you could also think the H naught is that sigma is less than or equal to 1/4. And this is all ounces, right? I should say that here. Ounces. Okay, so this is a case where it's stated as we would like it to be that the standard deviation or this particular parameter is no more than, which means less than or equal to. So up to 1/4, but no more. So the alternative, the thing we hope we don't have reason to believe in, would be that it's greater than 1/4. And that's, of course, 0.25, right, in decimals, which we'll use in a minute. So note, this is a right-tailed test. Okay. Let's see what I have here. Okay, so we're going to test it at alpha equal 2.5%. So alpha equal 0.025, right-tailed test, and we take a sample of size n equal 30. So right away, I know that I'm looking at chi-square with degrees of freedom equal to 30 minus 1, which is 29. And so my curve looks something like this. So this is where in that space there you want to draw in the curve, something like that. And if I go looking, I'm not going to put the table up again because of the fiasco last time, but you should be able to find in any table you use for chi-square that to get the area out here to be 0.025 with degrees of freedom 29, I'm getting that this value is 45.722. Okay. All right. What do we get for the test statistic? We take a sample of size n equal 30, and we get S to be 0.38. So the test statistic is, it's a chi-square random variable, and it is calculated as n minus 1 times S squared over sigma naught squared. That's 29 times 0.38 squared over sigma naught squared is 0.25 squared, right? And if you work that all out, you get about 67. Okay, so that would put us somewhere out here, right, in the rejection region. So we we reject H naught. Our conclusion is at the 2.5% significance level, I'm going to abbreviate so I don't run out of room here on my board, there is sufficient evidence to reject the claim that the standard deviation is, and I'll stress that I'm kind of thinking of, here's my null hypothesis, right? So there's sufficient evidence to reject this, that it's less than or equal to 1/4, so that it is only 1/4, or 1/4 or less, in other words. Looks like it's higher. So your dairy is going to have to work on increasing the precision of its machines that fill the milk jugs. So it looks like it's higher. But by that, I mean, what's higher? The standard deviation. So, yeah, okay. So I don't need to say that. Oh, and actually, we said it in terms of variance, didn't we? So this is wrong. It's variance, right? I said no, pardon me, I'm looking at the next problem. This is correct. This is okay. Standard deviation is 1/4 of an ounce. Yes, pardon me. I was looking at the next problem, and it's about variance. Okay, so this is good. Go ahead and read example 2 while I rub this out. Here, I'll get us started here. Okay, change color too. All right, so what do we have here? There are no federal laws governing how accurate vehicle odometer readings must be, but the Society of Automotive Engineers recommends that the variance for odometer readings after a 100-mile trip be less than 4 miles squared. And if we're talking about variance, it's got to be miles squared, all right? Your auto company, Poetic Autos, has just released a sedan called the Limerick, whose odometer has in the past not quite measured up to this standard. Your engineers just upgraded the Limerick's odometer, and you want to check to see if it now complies with the Society's recommendation. Okay, so with that in mind, what is the null and alternative? Well, initially, we want it to be less than 4 miles squared. And in the past, it hasn't. So assuming this new manufacturing process, or the new whatever was done to to make the odometer supposedly better, assuming it didn't work, the null hypothesis would be that the variance is still 4 miles squared. And again, we could say greater than or equal to 4, right? But let me stress, this is miles squared. We could say greater than or equal to 4, because what we hope then is that it's actually less than 4, that this new process is less than 4. And I also make a point here of noting that what we're going to do to work the problem is just like what we did for the last problem for standard deviation. There's no difference here. We're just going to do the same work. So really, we could think that our null hypothesis is sigma is the square root of that, which is 2. And the alternative is that sigma is less than 2. Okay, so you can do this either way. It doesn't matter. Anyway, we have going to pick a sample of size 40, so our degrees of freedom will be 39, and we're going to look at the 5% significance level. This is left-tailed. Okay, so when I draw this here, we're going to have this be chi-squared. Degrees of freedom equal, well, 39, but I think most tables don't have 39, so I'm going to use 40, and the curve is something like that, and it is left-tailed. So I come back over here, and I want just 5%, 0.05 area there, which of course means I want all this to be 0.95, and of course to use a chi-square table, that's what you have to look up. Area to the right, 0.95, and if you do that, you should get 26.509. 509. All right, so that's what you have there. And so you lay out a 100-mile course exactly, and you drive 40 of these limericks, exactly that 100-mile course. and you record what their odometers say. And we're again assuming that you get a normal distribution with mean 100, but standard deviation is, whatever. In our sample we get, let's see, I say our sample standard deviation comes out to be 1.7 miles. So we compute S equal 1.7. Or we could say, S squared is 2.89, is just 1.7 squared. It doesn't matter which you're thinking of here, right? But we get that as our standard deviation. So let's figure out the test statistic. Test statistic is a chi-square random variable, n minus 1, s squared over sigma naught squared. It is 39 over 2.89, times 2.89 over our variance that we have under the null hypothesis, which is 4. And this works out to be about 28.2. Okay, so that puts us, you're blowing, you can make this arrow a little bit nicer, but that puts us right there in the non-rejection region, right? So we failed to reject. So at the 5% significance level, there is insufficient evidence to conclude that the I should say to reject the assumption. We usually say this. Say that later. To reject our assumption or our claim. So reject that the variance is 4 miles squared. All right, so we cannot reject that. So it might not be less, okay? So, that's a bummer because we were hoping it would be less. But all is not lost, folks. I want you to think about what this is actually saying. We did get a sample standard deviation of 1.7. We got a sample variance of 2.89. That is less than 4, right? The point is, it's not enough less than 4 that it puts it out here where we're going to reject the null and actually believe that the population standard deviation is actually less than 4. So in other words, what we're saying is this sample variance is not statistically significantly less than 4. Right? It's less than 4, but it's not really enough that we really feel like we can claim we know for sure that the variance overall will always be less than 4. Or the mean variance would be less than 4 for the population. But this suggests that maybe if we did a bigger sample, we might be able to, if we might still have a standard deviation of, a sample variance of around 2.89 perhaps, but with a bigger sample, we know that we can get what am I trying to say here? We can get a result that is, what I'm trying to say is we might get a result that tips over into being statistically significant, that tips over into the rejection region, right? If we have a bigger sample, then this number will get bigger if that's the same, but so will our cutoff value for a higher degree of freedom. So it's possible that with a bigger sample, we might actually scoot over into where we would reject the null. So what I would do if I were reporting this, I wouldn't say, oh, darn, we didn't do any better. I would say, we need more testing. We need to do like 100 cars instead of 40 cars. All right. Because it looks to me like maybe if you used a bigger sample, it would come through to be statistically significantly less than 4, and then you could claim that, which would be good. Next one. I hope you started to read it. Standard deviation of men's heights is 2.9 inches. Let us test this claim at the 2% significance level. We know that men's heights are normally distributed. So this is an easy one. The null hypothesis is sigma is 2.9 inches. The alternative hypothesis is we're just claiming that we believe it is 2.9, and so the alternative is that it isn't, right? So this is two-tailed. Maybe the variance is bigger, maybe it's smaller. We're just saying that the alternative is that it is different. What does the picture look like? Okay. We're testing, let's see, we have degrees of freedom is, we're using a sample of size 60. Yeah, I say that here. Random sample of size 60 men. And so degrees of freedom is 59. I'm going to use 60 again because my table doesn't do 59. Alpha is 2%. Alpha equals 2%. So I got to do half of alpha over here because it's two-tailed and half of alpha over here, right? So I want this to be alpha over 2, which would be 0.01, and this to be alpha over 2 to be 0.01 as well. All right, so I got to find those two critical values. I look in my table on the degrees of freedom 60, and if I want an area of 0.01 to the right, I get 88.379. Excuse me, over here, if I want 0.01 to the left, I need 0.99 to the right. And that is, I'm sure you can do these, 37.485. I'm sure you can look these up. Okay. Test statistic. Where does our test statistic lie? Chi-square random variable, and we computed as n minus 1 times s squared over sigma naught squared. That is 59 times, what did we get? We got 3.1, right, for the standard deviation, yes. The sample standard deviation we computed to be 3.1, so we square that, divided by the assumed 2.9 squared. And when we work that out, we get about 67.4. That's good enough. So that goes, somewhere around in here, right? So it is in the fail to reject region. I about fail to reject, only to write it again. So we fail to reject H naught. So at the, 2% significance level, there is insufficient evidence to reject the claim that, try not to squeak so much, that the standard deviation of men's heights is 2.9 inches. There's insufficient evidence to reject that claim. So you might say here, it may indeed be 2.9 inches. Remember, when we fail to reject the null, we're not insisting that the null is true. I'm not insisting, therefore, the standard deviation is 2.9, right? Hey, our sample standard deviation was 3.1, which is not 2.9. Just kind of reminding you of things that we've looked at numerous times in the past. So in fact, it may be different. It may be a little bigger, the true standard deviation. The point is, this sample we got was not enough different from 2.9 for us to feel confident to say that we're going to throw out this idea, right? Okay, so we're tentatively still holding on to this idea, I guess. We're failing to reject it. Okay, I guess that's it. We'll stop here.